We're now just months away from the Vera Rubin telescope coming online. We're just a couple of years away from the Nancy Grace Roman telescope flying to space. Euclid has already begun. These three telescopes, ground and space, are going to be working together to map out to almost the very edge of the observable universe. They will help us understand the concentrations of dark matter, the effects of dark energy, at a scale that astronomers could only have dreamed of in the past. And yet, this flood of information is going to be almost too much. Petabytes of data that astronomers are going to have to churn through to try and make the kinds of measurements. And so they need to get prepared. My guest today is working to solve this problem for them. He's Dr. Michael Troxel, an associate professor of physics at Duke University, and he's the image simulation lead for Open Universe. Now, Open Universe is a gigantic simulation of the entire universe. But what Michael and his team did was take that universe and then convert it into what is expected will be visible to Rubin, to Roman, so that astronomers working with those telescopes will be able to get prepared for when that data comes. We talk about what it took to build a simulation like this and what steps were required to make it accessible to these different instruments so that astronomers can make some real progress. Now, we talk about that. We talk about simulations in general. We talk about the telescopes. And then we talk, of course, about what questions that astronomers have that they're hoping to answer and how their understanding of the universe will grow and expand as these new, incredible telescopes come online. So enjoy this conversation with Dr. Michael Troxel. Michael, I'm fascinated by these large-scale simulations of the universe done on supercomputers. When you run a simulation for the first time and you consume however many days of time on a supercomputer, and then the you get ding, simulation is complete. What's the first thing that you look for to find out if it's better?
Yeah, so when you're running these large simulations on a supercomputer, the work starts 6 months before you press go. Things like the HST Cosmos data, for example, which is the largest space-based data set we have at these sorts of depths. So it's really an iterative process over many months where we're checking every step of the pipeline, every step of the input, and then categorizing what we're getting out visually, numerically, running our pipelines on it.
But I wonder about emergent behavior in the universe at the largest scales. I mean, there's something about having everything put in. I know that, simulations got better when you included the interaction of neutrinos. They got better when you included the interactions of the stars and the gas and the dust and the dark matter and so on and so forth. And also at the larger scales. I mean, we have these large scale structures in the universe, the voids, the walls, and so on. Is there something special that emerges when the full simulation runs with both all of the inputs as well as sort of the largest scales that you're hoping to achieve?
Yeah. So it's in the way that you're talking about, it is really hard to predict exactly what you're going to get out. There are lots of technical elements to the models that we produce, and there are limits to what we can validate on those models. For example, we can check that the number of objects as a function of how bright they are is approximately right, matches what we've observed about the universe so far. We can measure how correlated different properties are in the simulation and how those look like for the real universe. But those are low-level values, low-level measurements in the sense that they only measure particular modes of information, very basic modes like the mean or number counts. And we did run into this when we produced this latest set of large simulations. All of those metrics looked great on paper. And then when you looked at the images, things just looked a little off in our first test round. We had lots more bright objects clustered together in what we call halos, which are the dark matter structures that baryonic things like galaxies and stars form within. And so things look much more spectacular or interesting in the images than the real universe is because there's all this bright clustered stuff. And we were able to build a feedback loop in. We saw this thing that looked emergently, like you said, a little weird, too interesting compared to the real universe, you might say. And we're able to go back and tune our numerical tests, our validation metrics, to catch what ultimately caused that for the main run. And this is one of those integration steps or validation loop tests that I talked about. Yeah.
But, I think when I talk about simulations, and, we see this in a lot of fields. I mean, it comes up in climate science all the time that, that what you just mentioned, this sort of process of looking at the final result, comparing it against your understanding of the universe, and then going, okay, obviously we need to tweak the simulation because we didn't get the right universe. That seems very, I think for most people that'll feel a little unproductive, but I think the goal though is now you can make predictions about the universe, about things that we don't know. So what, as you sort of complete this final version of the open universe, you have the universe in front of you at a resolution, you can zoom into any part of the universe that you want. Yeah. What are now the predictions that you're making about the universe that hopefully telescopes like Rubin and Roman are going to be able to confirm or deny?
Yeah, so there are kind of two ways that we use simulations. One utilizes bottom-up simulation of the universe, like you're talking about, where we take our best data set and we try and produce a universe that has all of the physics we know about in it, that ends up with some final universe realization that still matches what we know, what we observe the universe to be. The utility of that is that there's all the physics that we are unaware of, or you can even create universes that have slightly different physics that are still consistent with what we see if you want to test a particular model, for example. And we use those as test beds to understand what we can observe about the universe. We can do the same sorts of things we would do on the real data, but we have much larger volumes. We can create the entire universe or as large a section of the universe as we want if we have a coarse simulation. And those are used for developing models. We can even, for example, extend the regions of measurement that we can study. For example, gravitational physics is well understood on large linear scales. Linear meaning small perturbations in the curvature of space-time or the matter density. But when you want to look at the small scales that are getting closer to the size of a cluster of galaxies or individual galaxies, there's a huge amount more information there in terms of what we call number of modes, which are the number of Fourier modes you can sample in a field. But it's very hard to build an a priori analytical model for that information because things become very nonlinear. But we can make measurements of that information from simulations that match the real universe. And we can use that to build a model or a suite of models over some parameter space, some cosmological parameter space, to use when we study the real universe. The image level simulations that I do have a slightly different goal in that we can have all of this physics that exists in the simulations I just talked about, but we are simulating also how we observe the data, the instrument characteristics, how the photons that we would receive in the telescope get translated through the electronic system to counts data. And we use that in a slightly different way to prepare for future data or to calibrate data at a very low level. So our goal with the Open Universe Simulation Suite that we just made, combining Rubin Observatory data and Roman Space Telescope data, is to give the teams that are working on those experiments an opportunity to have data that has all the weirdness that their actual telescope data will have before they have that data. And that allows them to build the pipelines that will produce catalogs of objects or measurements of objects that we'll ultimately do science with, and to understand how we need to better calibrate that before we get to actually doing it on the real data.
So it's not just enough to simulate the universe. If you could fly around and look at any object that you wanted, it's about simulating the universe in a way as it would be perceived both by Roman out in space or Rubin through the soup of the atmosphere.
Yeah. My science field, weak lensing, gravitational lensing, we use, for example, to map where dark matter is in the universe. and we do this by measuring the shapes of objects. And so if a bunch of objects far away from us, their light travels to us, passes through structure along the line of sight. That structure, the photons or light rays, are going to follow the curvature of space-time. Space-time is locally curved around that mass, and that causes a deflection in the path or a distortion in the shape. And because all of those background galaxies' light travel through the same structure, they have a coherent distortion, and we try and measure that coherent distortion by averaging over the correlation of shapes of objects in the background. The difficulty is that it's essentially impossible to make an unbiased measurement of that. We're trying to measure the shape of objects that are just a few pixels across, that have a signal to noise of like 10 across many pixels. So if you just look at an image, they're barely visible. They're just a bunch of noisy pixels that look correlated. And just very hard to do it's very hard to extract the actual shape of any individual object in an unbiased way. So that's a function of the telescope. It's a function of how the optics of the telescope or the atmosphere also smear out and change the shapes of things through what we call point spread function, this atmospheric distortion or optic distortion. It's a function of the ultimate signal to noise of the objects, the number of photons that actually make it through the instruments for any given object, for some type of object or some flux, intrinsic flux of the object. And we really have to get all of those things simulated accurately to understand how biased that measurement is. And so there are ways we can kind of self-calibrate the measurement with the data, with techniques, one of which we call meta-calibration. And that gets us most of the way. But there are still things that we can't fully calibrate without reproducing the entire measurement on these simulations. And so this is an example of a case where we really need these large simulations to understand the characteristics of our measurement.
Oh, it's really interesting. So it's funny. So like we share pictures in our news and on the website of like really nice gravitational lenses and Einstein rings. But those are like the charismatic megafauna of gravitational lenses. They're the rhinoceroses and the tigers of gravitational lenses. But the reality is the vast majority, and the ones that you're going to be using to map the precision of dark matter, are going to be 3 pixels that are like a little bit distorted, and it takes really like you need to look at millions of them in together to sort of measure what is their average warping of. Oh, that's really interesting.
Yeah. And in fact, if you look at for example, the dark energy survey, which is another experiment I work on, if you look at the mask, so you can characterize which parts of the sky, which data we can use and which data we can't use. If you look at that mask that we use for the weak lensing measurement, not most, but a large number of the large blocked out areas of the survey are exactly those really bright, pretty galaxies that you see in popular photos online from HST, for example. The ones that are big and bright are too bright, too big for our sensitive cameras that we're using to do these very deep, sensitive weak lensing measurements. And so they're actually systematics to the galaxies that we care about, which are all the very tiny, low signal to noise ones, which are most of the objects in the image.
I think people have a fairly outdated notion of how well astronomers are able to measure the concentrations of dark matter today. Can you give us a sense of to like what level of precision we know where the dark matter is in relation to the galaxies that they inhabit, and sort of how that sort of narrows down the possibilities of what dark matter could be?
Yeah, so there are kind of three regimes where we measure or infer things about dark matter. One is on the very largest scales, the total composition of the universe. The total amount of dark matter, dark energy, standard particle physics material. In cosmology, we call them baryons, even though there are non-baryon stuff in there. Those broad categories are extremely well measured. First with the cosmic microwave background experiments like WMAP and Planck. And now, more recently, with low redshift universe probes like galaxy clustering and weak lensing, baryon acoustic oscillations, these current low redshift surveys that are going on. And there, you're really just measuring how much of the stuff in the universe is this type of matter. For example, dark matter. We know that very well. We can measure that value, that fractional constituency very well. Then something that has only recently been possible with low redshift galaxy surveys like the Dark Energy Survey is that we can take these hundreds of millions of galaxies in, say, an eighth of the sky for the Dark Energy Survey, and we can reconstruct these distortions in their shapes, map this distortion map in the curvature of space-time from all of the mass there, not just the mass we can see, the baryons, but also the dark matter. And we're actually producing maps on a coarse, maybe half a degree resolution scale of where projected on the sky, the 2D plane of the sky, all of the dark matter is up to around half the age of the universe ago. And we're creating these large-scale maps of the dark matter. And that's interesting because it tells you about how dark matter is clustered on large scales. And then there's a third regime where we look at dark matter, which is, like you mentioned, individual halos. We know that dark matter is gravitationally forming these high-density regions. This is where galaxies tend to form, clusters of galaxies tend to accumulate. And for those, we're looking at much more specific measurements of these distortions around specific halos, for example, or we're taking very large structures like clusters of galaxies or background distortions like the Einstein rings you mentioned, and we can really learn about the shape of the halo of the dark matter for individual clusters of galaxies or even individual very massive galaxies, for example. And we can do all of that with weak lensing, gravitational lensing, which is why I find it fascinating. But you can also use other specific types of physical processes to infer these different things, like on the larger scale, the CMB, on the smallest scale, galaxy clustering, or these strong lensing events.
Even on the small scale, you can use the Doppler measurements to track the motions of all of the stars in one galaxy, and then use that as a way to map out the quantities of dark matter around it. And so, sort of at the smallest scales and at the largest scales, we're really it's funny, right? Like, we don't know what it is,
yeah,
but it's the level of precision that it's being measured to is incredible.
Yeah. We can tell you exactly how much is in this part of the sky, but what it is, who knows?
Yeah. And so you mentioned like these half degree on the sky. So like the size of the moon-ish on the sky, you've got a map, a 2D projection of, are you saying like of all of the dark matter that is sort of behind it in a sort of conical slice all the way out to the end of the universe?
So we usually measure distances in redshift. So this is like a redshift of 1.2, which is about 6 billion years ago in look-back time. So we can infer the projected distribution of the dark matter anywhere between us and the furthest galaxies that we can observe with a survey like the Dark Energy Survey, which is that kind of 1.2 limit in redshift, or 6 billion years of look-back time. And so anywhere those photons have passed through that dark matter along the line of sight, we can learn about the cumulative distortions in the photon's path, which tell us the coarse distribution of the dark matter.
So I want to kind of re-ask my question, the one that I asked you earlier about, when the simulation starts up and then you look at the data and what are you looking for? But when Rubin comes online and begins producing its data, when Roman launches and begins producing its data, Euclid is already going and doing its version. And then there's DESI and there's other surveys. And so they're all working together to produce as much data as possible. What are you going to be looking for?
Yeah. So each of the surveys have their own strengths. unique strengths. And this is also true of the current generation of surveys. The dark energy survey observes a huge area of the sky, 5,000 square degrees. Rubin will be similar, except 10 times better in every way. It will observe half the sky at a much better resolution, depth. So Rubin is going to see half of the universe, and it's going to see that over and over again every few days, which is another transformative element of that survey, and that you get basically a time sequence of how things in the universe are evolving, which is really important for other ways that we study the universe, like through supernovae, for example. Then on the other end of the spectrum is a survey like Roman. Roman is in space, so it will see everything sharper, but you're limited to how much you can send up on a rocket in a single launch. So the telescope is smaller. It's not going to be able to view half the sky. It might view several thousand square degrees of the sky, similar to the size of the dark energy survey. But it's going to see much deeper, much sharper. And so a lot of the things that we worry about with something like weak lensing, where we're trying to measure the shapes of individual galaxies, as you observe deeper and deeper into the universe, there are more and more things you can resolve. Eventually, they start becoming stacked on top of each other, or overlapping in projection, which is what we call blending. So having a telescope in space is really critical for the sharpness of what it can see. It doesn't have to look through the atmosphere, so things aren't smeared out by atmospheric temperature gradients or turbulence. So we can better distinguish individual objects, and we can distinguish them much further away with a telescope like Roman. But then we have better statistical power from all of the objects, the area of the sky we'll see from Rubin. And so one of the goals for these sorts of simulation campaigns was really providing for the community simulations of these two instruments, because their true power is going to be when we combine that information, when we use the Roman Space Telescope to help deblend or differentiate individual objects in a statistical sense in the Rubin data, which is going to increase its ability to do weak gravitational lensing. Or vice versa. The Roman Space Telescope is observing in the near infrared, around 1 to 2 microns. That is difficult from the ground because water in the atmosphere absorbs that sort of light. But to do precision distance measurements with Roman, we'll need the optical information that we get from the ground, from the Rubin Observatory as well. And so there's this huge synergy that gets formed by the strengths of each survey. They're very powerful in different ways in their own right, but then the ability to learn how to combine the data, which is a non-trivial thing with the petabytes and petabytes of imaging we'll have, that's, I think, where these simulation suites that we've been producing really shine. We're enabling the community to start learning how to do that now, so that we can combine the strengths of these surveys when they launch or when they start.
Right. Because I know I'm going to be all over it. As soon as Rubin comes online, I'm going to be asking lots of questions, and I'll talk to astronomers and they'll be like, I don't know, I'm still downloading it. It's huge. Yep. I don't know. Yep. Talk to me in 3 years once it's done. But I'm, I can't wait for that.
Yeah.
So I want to talk about, like, with the Open Universe, with the simulation that you did. You had 9 days on this supercomputer. Will you have time to do another version, a more, like, maybe a more powerful version, a larger version, before these telescopes actually come online?
It's unlikely that we'll be able to do that before Rubin starts taking data in the next year or two. Roman is scheduled to launch still in October 2026, which is the earliest launch window it has available. It is possible that we'll do another round before Roman's launch. Mostly that depends on interest in the community, improvements to the input that we can make in that time, and the availability of computing resources. It's pretty rare to get the sort of opportunity that the Argonne Leadership Computing Facility gave us with the Theta cluster. So I'm hopeful that we can do that again. Certainly, we will need to once we have the telescope's data anyway, because this is all an iterative process. The best data we have now is not as good as the data we'll have from these next generation observatories. And so we will learn things about the universe that we'll need to fold into a new generation of better simulations at that point as well. But the campaign, I think, was a really great. It did a really good job of bringing the community together across the Rubin and Roman and NASA and DOE communities. We produced something that was, I think, very successful. In that there's a huge number of projects ongoing using the simulations already. And it really showed what we can do when we bridge traditional expertise from the DOE-funded community like the Rubin Observatory and the NASA-funded community like Roman. So my hope is that this is a good benchmark or demonstration of what we can do if given this sort of resource. So I do hope in the next maybe 3 years or so that we'll be able to do something better.
I think of it kind of like a video game when they release the sort of version 1.0 of their game, and then you have everybody play it, and then everyone gives their feedback on the things that worked, that didn't work, and then they release a new patch. And in this case, you've released version 1, and the astronomers are working with it, but really, you're not going to know whether you properly simulated the universe until they make their observations. So what will you be looking for to do, 1.1 once you've actually got all that data from Roman, from Rubin, from Euclid, from DESI?
Yeah. So when we model the universe, we kind of model the ideal average universe that could form, which is not the same as the universe we actually got necessarily. We call this cosmic variance. And within the universe, different parts of the universe evolve quite differently. They may overall have this average value of omega matter, which is 0.3 or something, omega dark matter 0.25 or something. But if you look in individual regions, that varies. The best large field data set we have to calibrate our simulations off of is the HST Cosmos data, which is less than a square degree on the sky, a very tiny part of the sky. So we don't know how representative that tiny part of the sky is to the whole sky. And so all of our calibrations have been trying to match the constraints from this tiny part of the sky. But once Roman turns on, in a matter of months, we will have tens, hundreds of square degrees of better than Cosmos data in some aspects that we can recalibrate against. We'll really understand the cosmic variance of that tiny field much better. And so even just turning the telescope on, the amount of data that Roman can take compared to something like Hubble or Webb, it will really revolutionize what we're able to calibrate or compare against in terms of this space-based photometric imaging.
To torture my analogy even further, you've from the game, it's gone through QA, so they've had a chance to play it and they found some bugs, but it's really till it actually meets the full cosmos will you actually know those answers. Do you have any like hunches? Is there stuff where you wish if you had double the compute time that you wish you could explore a couple of different variations on the universe to find something that maybe would both sort of satisfy some questions that you might have, but also maybe give some variety to the astronomers?
Yeah, so there are kind of two levels, yes, that I would say yes to. One is at the underlying simulation of the universe. I don't think that we've ever really had a truly what we call blind, and what we call blinding is really important in cosmology because this is an aside to explain what I'm going to say. Because we have one universe. We're not a particle physics experiment where we have a collider and we can collide millions and millions of pairs of particles and see what happens. We get one experiment, it's already done, and we can observe it once in an unbiased way. And so we really worry a lot more, I think, about observer bias or kind of subconsciously reinforcing the things that we expect. So there are sort of natural models for dark energy, for example. One is that it's a cosmological constant in Einstein's field equations, where it has a particular dark energy equation of state. It's really easy to expect that to be the truth because every experiment has been consistent with that. And so even without thinking about it, there are some deeply rooted expectations about things that the universe could be doing. So we have to be very careful about stepping back and not building in safeguards to prevent that sort of observer bias. And I think that one thing you could do with simulations is you could create universes that look like a cosmological constant in the field equations, or that look like something completely different that is entirely consistent with our current observations, but could be distinguished with this next generation of experiments. And I don't think anyone has really successfully done that sort of blind test on simulations where they can show that they really can infer what the universe is really doing when they don't know what the input to the simulation was. There have been attempts by many collaborations, I think, to do this in the past. I don't know that any has actually worked out very well, but that's one thing that we could do with these large simulation suites if we were able to produce multiple of them. The other is that when we simulate the instruments, we're simulating their specifications or their requirements. But when you launch a telescope into space, things rattle around, water evaporates, gets much colder, things change. Same thing on the ground. Over time, things evolve. And the sorts of characteristics in the instruments we're going to realize is going to be different at some level than what we've planned for, or what the requirements are. Some will be better, some will be worse. And so, especially for something like the Roman Space Telescope, as we're preparing the pipelines to calibrate the data, it would be really interesting to me to simulate a version of the telescope that is a little different in ways that the people at the Science Operations Center who are building the calibration pipeline don't know, and then see if they actually calibrate it properly. See if we can actually calibrate the weak lensing signal properly. If we don't know what the actual characteristics of the instrument are, which is the case will be in when we launch the telescope. So I think those are two kind of very different ways in which simulating more or multiple realizations of the data would be quite valuable in a scientific sense.
So going back to that, the first version that you talked about, you've got this simulation of the cosmological constant as an explanation for dark matter, but we see with the Hubble tension, we see a difference in the measurements of the expansion rate of the universe from the cosmic microwave background compared to the more closer Cepheid variables. And if you just took that as a given, we don't know why, but dark matter is this at the beginning and then this in the middle and then this now, run that through your simulation and see what it does. And you might get a different universe that will have enough subtle differences that you could actually make some kind of predictive, comparison when you actually put it in front of it. Is that a sort of good example of that?
Yeah. And people definitely do make these different types of simulations. I think the key difference here is whether you know what to expect out of the simulation in the same way we don't know what to expect out of the universe or not. Yeah.
And then on your second point, I think astronomers working with James Webb were surprised at how well they were able to align everything. And I think they got they're getting better data than they were anticipating. And so in the best possible world, in fact, the astronomers with Rubin, with Roman are going to need maybe something that's a little better so they can even distinguish it even more. And is that in your data? Could you, because if you've already done the compute to actually, are you computing their ability to observe this universe at the same time that you're calculating the universe? Or is that a post-training additional layer and you could produce multiple versions of that?
Yeah. So there's the underlying universe, which is the model of all the stars and galaxies and things. That's one thing. And that exists before the campaign that we did at Argonne. That on its own is expensive, and for this simulation, we reused existing in-body simulations, like the gravitational physics, the evolution of the universe. So we didn't have to recompute that. And then there's the telescope. What happens to the photons above the atmosphere through when they get converted to electrons and read in the electronics of the sensors. That's the process that we simulated at Archon in January. So that's done. Now, depending on the instrument, because we have different simulation pipelines for the Rubin Observatory and the Roman Space Telescope that use common tools that we've built over the years. But depending on the instrument, there is an element of what you talked about where we can kind of save intermediate steps and then reprocess things. So for the Roman Space Telescope, we save a version of the images, which is basically where every photon is before it goes through the instrument, or before it hits the sensor, for example. And then we have a second processing stage where we convert those photons above the sensor through the quantum mechanical processes that happen in the sensor to what we read out as electron counts or data units. So for some types of physical processes, we can resimulate, and we do resimulate the final images from those intermediate, we call true images, because they're just the true photon distribution. We can do that and tweak things about the sensors for the Roman Space Telescope. Depending on how your simulation is set up, that's not necessarily possible for all instruments. And some physical processes, you can't really change them without resimulating everything from the start, like the point spread function, for example. But we are doing some of that. We've in the simulation, the main images for the Roman Space Telescope we produce are kind of what you would expect to get after calibrating the images. There's another version of the images we can produce if people want to use them that have all of the craziness of the uncalibrated data, which is not useful for most people right now because there isn't a final Roman calibration pipeline now that people can use. So no one would be able to calibrate the data right now. But there are aspects of that we can do and will do as we iterate without redoing the whole simulation.
I mean, some of the most fascinating stories to me are times when astronomers working with these telescopes realize a clever trick. Whether, LIGO is a good example of this, where they figured out they could do quantum squeezing to get better resolution on the imaging of black hole mergers, of detecting the gravitational waves. And for ground-based telescopes, obviously, you can come in later and you can put in a better instrument. You can remove additional noise from all of the instruments, spend more time figuring out where things are, could be improved. Space-based telescopes, not so much, but there's some techniques people can try to adapt. And then I wonder if using your simulation, they can try different ideas. What if we, can we get a better place? And that's where that raw data might come in useful. Is they could try a bunch of ideas and then run it against a version of the data to see what their expected outcome might be. And so it sounds like it's another way to improve.
Yeah, that is my hope for what people can get out of these simulations of the actual data. We've got this, at least for the Roman Space Telescope, this true image that they can make measurements on, and then the image that goes through the sensors that they can make measurements on. So you can iterate comparing against those and hopefully improve what we'll be able to do with the real data.
It's two audiences. I mean, the one audience is the astronomers who are just going to get their picture in the pipeline. They're going to look at it and they're going to measure their gravitational lenses and call it a day using the telescope that they have. And then there's the people working on the instrument itself kind of going, how can we make this better? And then running the simulations against their simulations to see what could produce a potential better outcome. It's a sort of a nice virtuous circle. So Michael, what are you obsessed with right now?
Well, so right now my main focus is preparing for these surveys. The type of data that we're going to get from Roman is in many ways simply revolutionary for a science like weak lensing. There are lots of things you have to worry about from the ground, the atmosphere, messing things up that just don't exist in space. The Roman Space Telescope is in many ways an ideal instrument for weak lensing. That was one of its designs. And so we're in a completely new regime of weak lensing science with this mission. But there are also things that we'll have to do for the first time that we've never had to deal with. So there's a cost to sending things into space that are space ready, that can survive space for 5 years, where instruments don't enjoy their life in the radiation vacuum of space. And so one of the consequences of that is that space-based images have relatively large pixels compared to their resolution. And so the information that we get from a telescope like the Roman Space Telescope, the data is so good in some ways, the PSF is so small from the optics that it's smaller than the pixel scale. And so you can't actually, on a single image, map out what the PSF is. And we call this undersampling, because we can't map all the small scale features of the PSF. And so we'll have to combine many images together to reconstruct that subpixel information that doesn't exist in a single image. And that's not something that you have to worry about with ground-based data typically. So there's a huge regime change in how we have to deal with the data for weak lensing that opens up a whole new challenge. That's one thing. The other is that we're going to see so much deeper. So with something like the Roman Space Telescope. So we were thinking about dark matter or dark energy, figuring out what they are. If you have a cosmological constant, dark energy evolves in a certain way. Its energy density is constant per unit volume at all times. If it's a phenomenological field or something that is not just a constant like the gravitational constant in the field equations, then it's going to evolve differently. Its density will evolve over time. And so its effect on the expansion of space is going to change over time. With current data, we can't differentiate that. We're looking at a relatively small region in terms of time or distance in the space. And so measuring that evolution over time in the expansion rate of the universe, we don't have a very strong lever arm. And in that, we're not comparing very, very far apart instances in terms of space or time. But that will change completely, especially for the Roman Space Telescope, which is going to observe back 9, 10, maybe even 11 billion years ago. Now you have a lever arm that is basically the size of the observable universe, and we're going to really see for the first time how things are changing over time in a way that current telescopes just can't. And that's going to give us the opportunity to completely blow open these questions, because now instead of measuring how much dark energy there is, we're going to be measuring how much dark energy there is as a function of time. And that will really open up what we can learn about the model space, the physical features of what really dark energy is.
Or maybe even location.
Yep.
Yeah. Yeah. I mean, I think, like science always runs up against the very limits of its ability to observe. Like at a certain point, I think about, say, that like the searches for dwarf planets out in the outer solar system. Like if you notice, there haven't been a lot of new dwarf planets found because the current crop of telescopes are reaching the very limits of what they can observe. But when the next round comes out, then we're going to, within weeks of Rubin coming online, we're going to learn of probably many new dwarf planets and other objects out there in the outer solar system. And same thing when these first surveys start to come in, what was all at the very limits and the edge and the hints and it all just now just becomes easy to access. It's a pretty great, I mean, it's the same thing that we're seeing with Webb, where they're just like, oh, do you want the spectroscopy on a galaxy with redshift 14? No problem. Right. Here you go. And the kinds of things that Hubble required, a gravitational lens and low sigma to accomplish. So, it is. I know what you mean, that seeing stuff that was all, you had to really squint, suddenly all just becomes beautifully into focus. But then come the next questions, right? I mean, this process never ends. And so, you're going to have this resolution on the sun, but then here come all the new questions.
Yeah. And I think in some ways our imagination about what dark matter could be or what dark energy could be is framed by the limitations of what we can measure. I mean, differentiating a cosmological constant versus not a cosmological constant is a tiny thing theoretically. There are way more exotic things that could exist, but we've really been focused for decades now on just that one number. And now we're going to turn that one number into a whole field of numbers. And I think it will spur an entire new generation of thinking about the way we view these problems fundamentally.
Yeah. And it is funny how this is what astronomers want. Like, I think astronomers want this to be complicated and messy and interesting and move from just one number that you're like, what are you going to do? Right. To picking away at all of the little bits and threads and strings and stuff that you can actually start to make some progress again on our understanding of the cosmos and listen to what nature is trying to tell us. Good luck with uncovering all that. Thank you so much for your time.
Yeah, thank you for talking.
I hope you enjoyed this conversation with Dr. Michael Troxel. I'm going to give you some of my thoughts and impressions, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Bill, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modzo, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I know I've been talking about these telescopes for years, and yet we are now really just months away from Rubin coming online, just a couple of years away from Roman coming online, and all of these data are going to be dumped into the internet so astronomers can then start to work through it and start to make some questions. And it was right near the end of that interview where this really struck home for me that up until this point, based on the best observations that astronomers can do so far, we're just getting the very slightest hints of what some of the characteristics of dark energy are. We see dark matter well resolved in some places, but the entire universe, it's still a bit of a mystery. And suddenly, these instruments will be able to fill in all of the gaps. We will see the influence of dark energy from recent times all the way back to almost the beginning of the universe. We will see dark matter not in just this tiny little slice of the universe that Hubble was able to look at for a long period of time, but half the sky, and definitely a significant portion of the entire universe. What was a fairly rough number becomes an incredibly deep, nuanced number, both in terms of time, in terms of space, in terms of degrees in the sky, comparison between different instruments. And this will give what is a lot of arguments final understanding. And yet, of course, will open up new questions about the universe. And I can't wait to hear what happens